Hello and welcome to the continuation of fun things we're doing for conference-driven development. This is, I'm going to talk about how to run macOS on macOS for now, on Apple Silicon. So there's lots of apples inside apples. You need to do AI these days, right? Who am I? I'm Alex Graf. I'm a kernel hypervisor, whatever you want to call it, developer at EC2. And I basically build the cloud. That said, this is not related to the cloud. That was just a side project where I was like super excited to see how Apple did a few things and was like, oh, I want to see how that works. And the way I usually try to understand how things work is by rebuilding them in QEMU, at least when it comes to low-level tech. And that's how we ended up with this presentation. Small flashback. Last year, I gave a presentation on Hypervisor.Framework, what it is, how it works. If you want to run QEMU on macOS with hardware acceleration, what you do is you basically run QEMU, which calls a special thing called Hypervisor.Framework that gives you pretty low-level access to registers to run virtual machines, so that the macOS kernel can be fully locked down and you don't have to modify anything there and install your own hypervisor there. And then you can run a virtual machine with that. Now, what Apple also did in addition to Hypervisor.Framework is they released something called Virtualization.Framework. Great names, right? Virtualization.Framework is a library that calls a separate or creates a separate VMM process and has an RPC interface for you to communicate with that separate VMM process, which then goes and essentially takes over the role of QEMU, right? So Virtualization.Framework is basically Apple's version of QEMU as a library. And that one creates virtual machines and you can go and run Linux. Well, this talk is not about Linux. Turns out, Virtualization.Framework also recently, I think like 3 years ago, gained support to run macOS virtual machines on Apple Silicon. And that's what all of this is going to be about. So if you want to run Virtualization.Framework, there's a couple of tools there. I usually use macOS VM because that's in Objective-C. I don't know Swift. Most of the other pieces are in other languages, or proprietary. Parallels, for example, uses this. I think VMware Fusion is also working on a backend for Virtualization.Framework because that's the only endorsed way by Apple to run macOS VMs, and people kind of want to do that on their Macs. What happens if you want to use I'm going to use macOS VM as an example throughout the presentation on how to use this. You can use your others if you want. What happens if you try to create a virtual machine there is you first need to install it. So Apple doesn't ship installers anymore. What they ship are recovery images because everything these days is a phone. I'm not kidding you. Like literally, like you get this picture across the presentation. Everything is a phone. You basically get this recovery image that you would usually use to recover a phone, and you, instead of recovering the phone, you basically recover your virtual machine from there. So that's the installation flow. And what you get out of that is a root disk image, an aux image, a type of device description, and machine ID. And we're getting there on what those mean in a second. You can then take these and say, go, please, Virtualization.Framework, go and run this now, and then you get a virtual machine. Easy, right? Well, let's look a bit deeper down underneath the hood. The disk image is just a raw disk image that contains the actual contents of the disk. However, its root volume is encrypted. So usually, like by default, you couldn't just go and map it and read it. The aux image contains in VRAM. I don't know if you've ever used Macs or macOS. If you did, something they basically carried over all the way from PowerPC into now is an NVRAM concept where you had first open firmware variables and then UEFI variables, and now it basically is parts of some NVRAM storage that is virtualized with the aux image. It also contains a copy of iBoot. iBoot is the bootloader they use on phones and on new Apple Silicon Macs as a bootstrapping entity. We get to that one in a second as well. The hardware model is super obvious. It basically is the same as the -m flag in QEMU. There's nothing there. It just says, please use this particular device emulation version so that you can run older versions of macOS on newer versions of Virtualization.Framework. And the machine ID is literally a single variable, which is the ECID. We're getting into what the ECID is in a second. if you look at macOS, the underlying kernel is the XNU kernel. Well, we usually are used to having a single kernel for everything there is, but and that is the case for x86, XNU. But on Apple Silicon, what they did is they basically changed that mentality from a single kernel away to multiple kernels depending on your generation. So you have the M1 kernels, the M2 kernels, the M1 Pro kernel, the M1 to M2 Pro kernels, and you see like there's something that looks different here, right? This one doesn't look like a bare metal kernel. Well, it turns out what they actually did is they introduced a completely new device model that is not the real machines at all for virtualization, and that one is part of the stock macOS images these days. So if you run macOS, you have a full environment on there that is able to run on virtual machines. It's always shipped. But what does this VM Apple thing look like? What is it? Well, turns out it actually is pretty standard. Like you have CPUs attached to this device model. You have a normal interrupt controller. It basically uses the Gig V3. You have, which is very different from real Apple Silicon, by the way. I don't know if you know the internals. You have normal RAM at a fixed offset, simple. You have a GPIO controller for the power button, the same way that we do it on the Virt machine model. You have a PL011 standard ARM serial device. You have a normal RTC, the one that Will just described, also lives right here. Also, newer versions now do a PV one. And you have actually the QEMU PV panic device lives in that VM Apple device, but I'm pretty sure they prototyped this on a well-known hypervisor. And then you have a pretty stock PCI Express bus. Sorry if you cannot see this bottom down as well. But down here it just says PCIe. They have a pretty standard PCIe bus. The major thing that's slightly awkward is that they don't do interrupts whistling. But meh. The rest is standard. But there are some non-standard devices, things that are particular to the VM Apple device model. Obviously, you have a very special case boot RAM that brings up this particular device. We get to that in a second. You have a special config region. You have the backdoor interface, is what I called it. I'm sure there's a different name for it, but the most obvious one to me is literally backdoor interface. You have a graphics, virtualized graphics entity, AES engines. It's a phone. And a special Apple Virtual block implementation, which is, I'd say, 95% compatible with actual Virtual block. So if you look at the booting story, how do I boot this device, which explains the first three devices we're looking at. When your CPU comes up, it runs the boot ROM, like everything else, right? Well, the boot ROM turns out to be called AVP booter. I don't know what that stands for. Apple Virtual Platform, no idea. And it lives in this path on any macOS installation that you have. It's a special build of iBoot, so the same standard bootloader they use everywhere. And the only purpose it has is to access the config space for some configuration purposes, and then that backdoor interface to basically read out stage 1 from the aux volume. Once you read out stage 1 from the aux volume, it shows you a nice dump on the serial port. That one comes up and reads stage 2 from the root volume. So now you load stage 2 from the root volume, which comes up, shows you a nice splash screen on the serial port, and accesses the root volume again to go and read out the actual kernel to boot the XNU kernel and it jumps. It's blazingly fast, like all of this happens in, I don't know, a couple of milliseconds, right? But you'd always have this boot chain going from boot ROM to the aux volume, which would be your flash, your non-volatile storage, non-volatile flash storage on real systems, to something that is on the NVMe disk on real systems to the XNU kernel. So they basically modeled the exact same flow you would have on real hardware, on phones, on Apple Silicon Macs, also identically in the virtual machine, which is good. It means less divergence. But what is this config thing, right? Like what is in there? Well, it turns out it's really just a shared memory region. It's like a 16 kilobyte region of memory that is directly mapped into the guest. It contains things like how many CPUs do I have, how much RAM do I have, am I running in emergency boot mode to recover, or am I running in my normal boot mode? Uh, what is the serial number of my device? What is the CPU name of my system? So it contains a couple of things, and ECID, that's the important one. So ECID is very particular when it comes to Apple. It's the exclusive chip identification number. So that one exists in every single Apple SoC that you will find, and they're all unique. So this is how Apple ties the flash of your system to a particular phone, so that when you take off the flash, you can't just go and read out data from someone else. That's how they protect your data on your phones. And because of that, it basically by default always is used as the encryption key for your root volume, which makes it super annoying. It essentially means you cannot take a root volume from one device and put it on from one virtual machine and attach it to another virtual machine, because as soon as the ECID is mismatching, you're toast. Like you just cannot access any of that data. So you always have to carry the ECID around as well. So we cover those. Let's look at virtualized graphics. One thing Apple did with Apple Silicon, which is a break from any previous generations of macOS that I'm aware of, is they make 3D rendering mandatory. So in older versions, in PowerPC, there was no 3D rendering until later on x86, they had 3D rendering as a software rendering fallback backend. So you could basically bring up everything in 2D only, and then it would do things like LVM pipe internally to do 3D rendering. For Apple Silicon, they basically decided to get rid of all of that and only do real 3D rendering. And the way they do real 3D rendering is by something called Virtualization.Framework, which is another library you can call that then establishes that device interface. And that's what, for example, VMware uses when you do macOS on x86 on macOS. Then they also get 3D graphics through exactly this interface. That one is that simple from a usage point of view. Slightly annoying from a not running on macOS point of view. What you do is you're basically forwarding any LMAO request to this virtual device, to the library. The library then has a callback to say, hey, I kind of want to have access to this guest memory. And then they just establish some communication channel, a ring buffer, something, and keep going. And you're completely out of the picture as the VMM. You just don't know. What you get out of that is a metal shader that you can basically render onto a screen and then show the contents of that graphics device. So if anybody is interested in reverse engineering, cool target, really, you should look at it. AES engines. So every phone has an AES, or every modern phone at least has a modern Apple phone has an AES engine. It's the device that's virtualized in VM Apple is exactly the same device as in every iPhone and iPad and whatever you have out there. It basically is used on boot and for other things to hash data, to either create hashes for signatures or to validate signatures of things. It contains embedded keys. You can also configure your own keys. I don't remember if it actually uses that feature. But it mostly uses the embedded keys. I do hope these keys are slightly more random on real hardware. They're not very random on VM Apple, but I'm very fortunate. Like I'm very happy for them to keep it simple, because otherwise it would have been much more pain to actually reverse engineer all of this. So if you cannot read in the back, the keys for slot 1 is 1, the key for slot 2 is 2, and the key for slot 3 is 3. Those are 6-bit values. Cool. So that leaves only the VirtIO block device, which is particular. The Apple VirtIO block device is pretty much a standard VirtIO block on a different PCI device identifier, so that it doesn't collide with a normal VirtIO block number space. And it has a hard-coded Apple device type identifier at a fixed offset of the config space, which means since they didn't update the spec to have that included, they now collide with the zone extensions, and now we have two different values at the same location. You can only use one over the other. They also introduced a new block command, which I inferred as this is basically a trim with 0. So You have a clearly defined command that just says wipe this data. The patches are on the list. If you want to review today, tomorrow, over the weekend, by all means, have a look. That's super simple. You see it's like 12 patches, I think. It's not a lot. It's also not a lot of code. So enabling all of this virtual machine framework, virtualization framework, VM Apple backed device model is like less than 3,000 lines of code. It's not. It's simple. It really is simple. Okay. Paulo just said the backdoor interface smells like a 15-year-old back QEMU code. I'm not sure. It may. It may. I don't know who actually was the mind behind building this device model, so there could be overlap. I don't know. So how do you use all of this? Well, if you have these generated images from Virtualization Framework where you went through the installation step, we don't do installations on QEMU now. If you have these files, then you take them and you pass them into QEMU. You need to pass them twice because we need to pass them once into the backdoor interface and once into the actual virtual block interface. Backdoor interface for iBoot, actual virtual block interface for XNU and beyond. So you take your root device and pass that in. You cut off the first 16K of that aux image and then pass it in as a device. Then we ignore the hardware model, that's basically just -m. And then we extract the machine ID from that encapsulated, mangled, whatever thing. So it's a plist, it's an ECID value in a plist in a base64 encoded variable of a JSON inside a JSON, I think. Either way, you run the script and you can just get the ECID. And then pass that in as a UUID parameter to the machine model. Eventually, the command line looks kind of like this, right? You pass in the VM Apple as BIOS, you pass in an actual UUID, you pass in the P flashes, you pass in the drives, you say use HVF. There's no way right now to use this with anything but HVF, and off you go. Which means we can now take a look and see if the demo gods are pleasant. There we go. So here, can you read this? Probably not, right? I don't know how much you have to read because most of this is going to be graphical, but I will build a small run script to do all of the cutting and whatever myself and extracting of the parts. The way it's easier. But you see iBoot coming up, right? So we have iBoot. So over here is the AVP booter printing some debug info. Then you have iBoot stage 1, print some debug info, iBoot stage 2, print some debug info. And down here, the XNU kernel is starting, and did not configure this VM to emit serial output from XNU. Otherwise, you would also see that there. And then you have a normal macOS virtual machine running that is slightly unhappy about the screen size. And you can use it like you usually do with any of the virtual machines you have. You can browse the internet if that loads. If you're actually connected to Wi-Fi. Am I connected to Wi-Fi? Oh, I see. That's why. Oh. So it just uses Virtual.net with a normal backend. This is just using Slurp for me on the host, but I'm not online. It did work in the in the hotel room. So what issues do we still have outstanding? I hammered at it a couple of times. I never really managed to get a keyboard working properly. If you pass in a USB device with a USB keyboard instead, you get like hanging keys sometimes. Something is off with the interrupt somewhere, I think. Virtual keyboard doesn't work. The Virtual tablet thing works just fine. I don't know. It's something to debug eventually. There's no access to the total store ordering feature of macOS. So macOS can switch individual processes and even virtual machines to enable total store ordering for x86 emulation. And that's a private entitlement which you cannot do as a public open source project, so you don't get access to do your own total store ordering. So we don't get Rosetta. It's running on macOS only right now because of two reasons. One is it really requires an Apple Silicon device with HVF. HVF handles a few things in kernel space that are particular to this platform. And it also requires Virtualized Graphics Framework, which you don't have anywhere else, unless somebody in this room or somewhere else on the stream or wherever would be interested in figuring out how exactly it works, and instead pipe it into, I don't know, like a Vulkan API. Would be great. It also currently uses the proprietary AVP booter, which is kind of bad. Like, you don't want to use a proprietary initial early first boot firmware. We do have C BIOS, we do have open BIOS for exactly those reasons. It should be trivial to rewrite and do that, just do our own copy. Cool, with that, questions?
So would the total store ordering be possible if you disable system protection or SIP?
Wait, the speaker is right behind me, so I don't actually hear you. Say again?
So you're saying the total store ordering is not possible without permission from Apple, but would if you disable SIP, would it then be possible? Or
okay, I grasp Rosetta, Apple, something, and disable. Oh, I see. If you disable SIP, if you disable SIP on macOS, you can give yourself that entitlement, because then they no longer check for every single permission check for entitlements. They remove a few. Worst case, you just disable Amphi. And then you can do some changes to QEMU to basically, when the sysregs to enable Rosetta get called, you just ignore them and always enable TSO for the VM. So it would be possible with if you disable security, yes.
Yes, I have two questions. First question, can you run iOS, like phone images in this VM as well, or only macOS?
I think the honest answer is I don't know whether the phone images actually contain VM kernels today. If you would ask me for my hunch, looking at the market share and sizes of what Apple's revenue is, I would be very surprised if they didn't use this technology to eventually build virtualization for older versions of iOS.
And the other question would be, in your change list for your patches, I saw there were changes to RISC-V vector, RISC-V interrupt controller. I was wondering.
I think there was just a file path something, or an API change. That's just a generic tree wipe thing. There's nothing particular about RISC-V at all.
Okay, yeah.
It's
Thanks.
just like you had to touch some file just to plump through some information somewhere.
Okay, thanks.
Okay, thank you.
All right, thanks.